So if we are looking at 4.5 part 2, then first we're going to look at domain. When I look at this function, it should be pretty clear that we cannot plug in 0 into the denominator. So that means this will be my domain. When I look at x-intercepts, the x-intercepts are where y equals 0. So before I do anything, I think it's going to be easier to solve y equals 0 if I can turn it into a fraction equal to 0. So I take this, I get common denominators, and then this would be my new version of y. It's going to be much easier to use as I work. So for this thing, to find out where y is equal to 0, I set the numerator equal to 0. I get this. Then using the quadratic formula, you end up getting non-real solutions. So no intercepts. But then the y-intercept is where x equals 0. I think you can also, again, tell it's going to be undefined. There's going to be no values. When we look at vertical asymptotes, that's where the denominator equals 0. Again, I think this form of f that we created is going to be much easier to use. When I set that denominator equal to 0, I find out that x equals 0 is a vertical asymptote. Now, for horizontal asymptotes, I think it's pretty clear that this is going to be a better form to use, because as x goes to infinity, these go to 0, and you're just left with 1. So in the long run, y equals 1 is our horizontal asymptote. So now, increasing, decreasing, we take our derivative. When I do, I get this. So the first thing we do is rewrite these fractions as negative exponent, so that when we take the derivative, we get this. Then that means we have this, but then we can use a well-chosen 1 to get a fraction, because we know when we're setting derivatives equal to 0, we like fractions and factors. So if I set the top equal to 0, I get this. If I set the bottom equal to 0, in other words, where's this undefined, I get this. So this is really my only possible critical value, because x equals 0 means it cannot be a min or a max. It's a vertical asymptote, as we found out earlier. But we're still going to use that 0 to partition in step 2. And so that means when I look at this, I can now use that partition to chart. When I do, I use my numerator and denominator. So here's my numerator goes here, my denominator goes here, and so that tells me about f prime and f. So this would be enough to tell me about increasing, decreasing, and constant. But then I need to show that the derivative changes sign at -2. That's why we have a local minimum, because it changes from negative to positive. Then when we look over here and talk about concavity, we are talking about the second derivative. So we take the derivative of our first derivative and we get this. Doing a little bit of algebra, we get this and then this. So from here to here, this is just algebra. And then from here to here, this is factoring. Okay. So maybe what I should say is from here to here, we distribute, right? And from here to here, we combine like terms, and then we factor. So now we cancel some stuff out, and this is the form of the derivative, the second derivative that we will use. So we find out that -3 and 0 seem like they're going to be critical values, but remember, 0 is a vertical asymptote. So when I draw that thing, I'm going to make sure that at 0, it's clear it's a vertical asymptote. So it cannot be an inflection point. Cannot be an inflection point. So then when we chart, we get this, making sure to put our denominator and numerator. This is always positive. That makes it easy. So we get this. So it looks like the second derivative changes sign at 3. So that's why we have an inflection point right there. Putting that all together, the picture should look something like this, where this is our horizontal at 1, this is our vertical asymptote at 0, and then at 2 is a little minimum. So we know that it's what is it doing? We've got this change of concavity here, right? So we look back at increasing, decreasing, and so it looks like we are decreasing to -2, and then we're increasing. So decreasing to -2, and then increasing, and then it looks like we're decreasing over here in terms of increasing, decreasing. Then for concavity, we're concave down until -3, and then concave up after that. So that's why we know our shape should look something like this. So we need that inflection point in there. And then this is concave up. Okay, so then 15, if we've got y is equal to this stuff, well, for the domain of this thing, so for the domain, we worry about square root of a negative or stuff over 0. So here, denominator equals 0 lets us know that x squared is equal to -3, but that happens nowhere. So our domain is all reals. X-intercept is where y equals 0. That's where we get this. Similarly, y-intercept is where x equals 0. So this is our only intercept. The vertical asymptotes, where our denominator is equal to 0, that doesn't happen anywhere. Then remember, the horizontal asymptotes are the limit as x goes to either plus or minus infinity. So this thing is infinity over infinity. We can use L'Hopital's rule and get 1. So 1 is a horizontal asymptote. For increasing, decreasing, we take the derivative and get this by the quotient rule. And then from here to here, we distribute. Then from here to here, we collect like terms. So this is the derivative that we're going to use. It tells us that 0 is our only possible critical value. So when we chart, making sure to use the numerator and denominator of our derivative, we find out that the first derivative goes negative, positive, which is decreasing, increasing for the function. And so we have a local minimum at 0. So that's all I would need to see. In terms of concavity, the first derivative gives me this. So what did we do? So then from here to here, we distribute here, this 2x. So we take this, actually we don't just distribute. I'll just say simplify. We just multiply together this times this times this times this. That's all I've done to get this right here. Why does that make sense? Well, then from here to here, we factor out x squared plus 3. And we get our simplified version. Why is that great? Because that second derivative, either equals 0 or is undefined, is going to tell us our critical values. When we do that, we get plus or minus 1 at x are only points that are going to break up our number line, partition it. So then when we chart, we get this. And notice second derivative changes sign at -1 and 1, and those are allowed in my function, so those are inflection points. So when I draw it, I know that I'm decreasing and then increasing. First I guess I draw my horizontal asymptote. And then we know that we are decreasing and then increasing. But then, what else did I notice? At -1 and 1, those should be inflection points. So this goes down, down, up. This goes up. Yeah. So it goes up over here and then down. That's why that's an inflection point. So we have concave up to concave down to concave up is an inflection point here. Then in the long run, we're just making sure that we get closer and closer to horizontal asymptote. So notice the way to do this step by step is to think about the increasing and decreasing. Think about those horizontal and vertical asymptotes. We only had a horizontal. Then if you think about concavity going down, up, up, down, That's why we need these inflection points. We also had a local minimum here. Okay. And that looks like it's it. Great work.